All right, let's get into it. Today, we are diving deep into the world of the atom, the stuff that makes up, well, literally everything. But this isn't going to be your standard textbook lecture. Nope, we're going to treat this like a genuine detective story, following the clues that led scientists to crack one of the biggest mysteries of all time.
And right off the bat, here's the central puzzle of our entire investigation. You, me, the device you're watching this on, it's all made of atoms that are almost entirely empty space. So, what gives? Why doesn't your hand just pass straight through the table? This is the paradox we are here to solve.
You know, for centuries, the smartest people on the planet were convinced that the atom was the absolute smallest thing you could get. Just a tiny, solid, unbreakable ball. But then, clues started popping up, suggesting that wasn't the whole story. Turns out, there was an entire secret world hiding inside. And here they are, our first pieces of evidence, the key players in this mystery. You've got the tiny negative electron, found by J.J. Thomson, just zipping around outside the center. Then, packed into the core, you have the positive proton, discovered by E. Goldstein, and the neutral neutron, found by James Chadwick. So, with these three particles identified, the million-dollar question was, how in the world are they arranged?
So the first person to really take a shot at solving this was the guy who discovered the electron, J.J. Thomson. And he came up with a theory that, honestly, was pretty clever and seemed to make a whole lot of sense at the time.
He called it the Plum pudding model. Just picture a big blob of positive energy. That's the pudding. And then, scattered all through it are the tiny negative electrons. Those are the raisins. Or, hey, think of a watermelon. The juicy red part is the positive charge, and the seeds are the electrons. A really simple way to imagine it, right?
And you know what? This model was a huge deal because it solved one major problem beautifully. It explained why atoms don't have an overall charge. The positive pudding and the negative raisins all balanced each other out perfectly. It was a really neat solution. But, as every good detective knows, your first suspect is rarely the right one.
And this is where our story gets a massive plot twist. Enter our next detective, a guy named Ernest Rutherford. He sets up this experiment that he thinks is just going to prove Thomson's model correct. Instead, it completely blows the case wide open.
So, Rutherford's plan seems simple enough. He decided to fire these tiny positive bullets, called alpha particles, at a ridiculously thin sheet of gold foil. Now, according to the plum pudding idea, where all the positive charge is spread out and soft, those little bullets should have just zipped right through, no problem.
But what he and his team saw was, well, it was just jaw-dropping. Let's look at the evidence. First off, just like they thought, most of the particles flew straight through. Okay, conclusion. The atom is mostly empty space. Check. Second, a few of the particles got knocked a little bit off course. That suggests they got close to something small and positive that pushed them away. But then there was the third clue, the real shocker. A very, very tiny number of these particles didn't just get deflected, they hit something and bounced straight back.
And when I say tiny, I mean it. We're talking about roughly 1 in every 12,000 particles ricocheting back. This was the clue that just completely destroyed the plum pudding model. I mean, for a particle to bounce back like that, it had to have hit something incredibly small, incredibly dense, and packed with a powerful positive charge.
You can just feel the astonishment in Rutherford's own words right here. It was completely unbelievable. And from this one bizarre observation, he figured it out. All the positive charge, and almost all the atom's mass, had to be crammed into this tiny little core at the center, which he named the nucleus.
So, with this new evidence, Rutherford proposed a brand new model. You got a tiny, dense nucleus in the middle, and the electrons are orbiting it like planets around the sun. It was an amazing leap forward, but it had one huge fatal flaw, at least according to the physics they knew at the time. Okay, so here's the issue. The laws of physics back then were pretty clear. If you have a charged particle like an electron moving in a circle, it should constantly be giving off energy. And if it's losing energy, it can't maintain its orbit. It should spiral down into the nucleus in less than a second. So, think about what that implies. It means atoms should be completely unstable. They should just collapse. But they don't. The world is still here. So, there was still a major piece of the puzzle missing.
The case had hit a wall. The atom was in crisis, seemingly impossible. So, our detective story needed a hero. And that hero was a physicist named Niels Bohr, who showed up with a radical, almost magical new idea from the super weird world of quantum mechanics.
Bohr's solution was just brilliant. He basically said, what if the old rules don't apply here? He suggested that electrons can't just orbit wherever they want. No, they're stuck in very specific, fixed paths called energy shells. And here is the mind-blowing part. As long as an electron stays in one of its assigned shells, it does not lose energy. It just doesn't. And with that one bold idea, that single rule break, the atom suddenly became stable. The model was saved.
So, not only did Bohr fix the atom, but his model did something even more incredible. By arranging electrons into these neat little shells, he accidentally cracked the code for all of chemistry. He figured out why atoms stick together to form, well, everything.
And it all comes down to a concept called valency. You can think of it as an atom's personality. It's desired to connect, and that desire is totally controlled by the electrons in its outermost shell. See, atoms are kind of like us. They just want to be stable, or happy. And for an atom, happiness is a completely full outer shell of electrons. They'll do anything, give, take, or share electrons to get there.
And the logic is actually pretty simple. It's all about finding the easiest path to that full shell. If an atom only has, say, 1 or 2 electrons in its outer shell, it's way easier to just get rid of them. But if its shell is already almost full, it's much easier to just grab 1 or 2 from another atom to finish the set. This fundamental drive is what chemical bonding is all about.
Okay, one last piece to our puzzle. It turns out that atoms of the same element aren't always identical. They can come in slightly different versions or have different faces, and understanding these different versions is a really big deal in the real world. The two big variations here are isotopes and isobars. The easiest way to remember this is to think about families. Isotopes are from the same family. They have the same number of protons, so they're the same element, but they weigh different amounts because they have more or fewer neutrons. Think of them as siblings. Isobars, on the other hand, are from different families, different elements, that just happen to weigh the exact same amount.
And this stuff really matters. This isn't just theory. A special isotope of uranium is what fuels nuclear reactors. Cobalt-60 is a powerful tool doctors use to treat cancer. And carbon-14, well, that's like a time machine. It allows us to figure out how old ancient artifacts are, unlocking secrets from thousands of years ago. These different faces of atoms are absolutely essential to our modern lives. And that brings our whole investigation right back to where we started. If you and everything around you are made of atoms that are almost entirely nothing, why does anything feel solid at all? Well, the answer isn't in the stuff itself, but in the invisible forces acting between it all. The repulsion between the electron clouds of different atoms is so incredibly strong it creates the perfect illusion of a solid surface. So the solid world you can touch and feel, it's basically a force field. A pretty profound thought to end on, don't you think?